How can a truck engine exceed 1 million kilometers without ever being disassembled? The doubt arises immediately when one faces a heavy-duty vehicle with that figure recorded on the odometer for the first time, because it seems almost inevitable to think that an engine subjected to such a load working day and night should be on the verge of collapse. But in the case of these trucks, the opposite happens, and that is where the real surprise emerges. Even after covering distances equivalent to several trips around the planet, their engines continue running smoothly, without strange noises, without loss of performance, or evident signs of fatigue. And this resilience is confirmed in everyday situations, in any workshop where a truck comes in for a routine check while the technician verifies fluid levels, examines filters, checks pressures, and observes the engine's behavior at idle. There, everything indicates normality, no signs of critical wear or unexpected vibrations appear, nor are there indications that the machine is near the end of its useful life. For those outside the world of transport, this situation may seem incredible, almost an anomaly, although for professionals it is simply the usual because they know that these engines are built to withstand long workdays, thousands of hours of continuous operation, and working conditions that paradoxically favor their durability when properly managed. That apparent naturalness has an explanation that begins in their very conception, from the construction philosophy to the way they are used and maintained, where each part is part of a system designed to last. Then a key question arises: what essential difference in the way a heavy engine works compared to a light one explains such resistance capacity? It is not in an isolated component nor in a hidden trick, but in the way these engines are designed to operate. Unlike light engines that need to run at high RPM to generate sufficient power, a truck engine develops its force at low revolutions and maintains that pace steadily under a clear principle. The slower and more stable the speed, the lower the accumulated wear and the greater the preservation of its internal components. This logic becomes clear when we observe the operation of one of these engines because what stands out is its mechanical serenity. The usual operating speed is low and remains constant over long distances, without abrupt acceleration changes that disrupt its balance. Each crankshaft rotation implies less impact on pistons, rings, and connecting rods, so the parts are not subjected to the repetitive stress of high-speed operation, which translates into prolonged service life. Internal friction decreases along with the gradual heating that usually affects smaller engines. This way of working is not accidental. It responds to a structural design aimed precisely at generating high force with few revolutions, where the piston stroke is usually longer, the displacement greater, and the combustion chamber is designed to withstand high pressures that produce continuous and robust torque. Thanks to this configuration, the engine can move tens of tons without forcing itself, and while in a light vehicle power is obtained through rapid accelerations, in a truck the response is based on force available from very low RPM, which reduces sudden demands and maintains a more uniform performance throughout the workday. This sustained behavior has direct consequences on durability because an engine that runs slowly does not subject its components to such frequent stress cycles and keeps its temperature within more stable and predictable ranges, allowing lubricants to circulate more effectively and maintain their properties over longer operating hours. In this context, metal wear decreases as each element works within a more controlled environment, and by reducing the risk of sudden overheating, the entire internal structure suffers less fatigue, so operating at low revolutions becomes an invisible but fundamental ally to reach resistance figures that surprise even those familiar with heavy transport. This advantage becomes even more evident during long hours on the road, when the engine maintains an almost calm rotational speed and stays within its optimal zone, without jolts or unexpected variations, in a type of driving that fits perfectly with this continuous operation. Since there are no constant stop-and-start cycles or abrupt changes in load, the assembly experiences less thermal stress and fewer internal fluctuations, which favors the stability of the lubricant and prevents particles and residues from accumulating aggressively, turning the engine into a work tool designed for continuity rather than momentary effort. Once this operating dynamic is understood, it is logical to ask the next level of explanation: how are these engines physically built to withstand such a level of effort during hundreds of thousands of hours of continuous operation? To understand this resilience, one must look at its internal architecture, where from the very beginning the design prioritizes structural solidity over any compromise with lightness. In this structural approach, these engines do not aim to be compact or lightweight, but solid, stable, and capable of absorbing immense loads without deforming or losing efficiency. And that is the foundation that allows a heavy engine to work day after day without showing signs of premature fatigue. The heart of this robustness is found in the engine block, which in a truck engine is a massive cast piece, specially designed to withstand high internal pressures. Each wall of the block has a remarkable thickness and is molded to resist vibrations, torsions, and thermal shocks. This structure not only supports the moving assembly but also acts as a barrier against deformations that could compromise the alignment of the crankshaft or the cylinder liner seats. In heavy engines, these liners are replaceable elements that facilitate long-term maintenance, so instead of changing the entire block, it is sufficient to replace the internal wear surfaces when the time comes. The same logic of robustness appears in the moving assembly, where the pistons are large and made of materials capable of withstanding very high temperatures and pressures without losing dimensional stability, because their size is not arbitrary but a necessity derived from the enormous force they must transmit. The connecting rods that link the pistons to the crankshaft follow the same criterion, forged from special steels that combine mechanical strength and toughness, while the crankshaft itself is a large and heavy piece designed to withstand millions of torsion cycles without showing cracks or deformations, so that each of these components is designed for intensive, continuous, and demanding use. The same concern for durability is reflected in the manufacturing tolerances, where clearances are calculated to allow materials to expand with temperature without risk of seizing, in an engineering approach aimed at ensuring that even under sustained loads, all components maintain predictable and stable behavior. While many light engines are designed seeking volumetric efficiency and weight reduction, heavy engines are conceived to survive, with parts that do not work at the limit but within wide margins that avoid excessive stress and significantly reduce long-term fatigue. This capacity to withstand continuous effort solves one part of the problem, but it leaves another equally critical dimension, which is the internal health of the engine while it works for hours without rest. Because bearing the load is only one side of the challenge, but the other is staying in optimal conditions without heat and friction deteriorating it from within. So how does such a massive engine manage to remain in optimal condition without overheating or wearing internally during entire workdays? The answer is not in the mass of the block or the size of its components, but in the systems that keep it alive while working, in those mechanisms responsible for controlling friction and dissipating heat, which act in a coordinated manner to protect the internal surfaces and ensure that each part operates within the intended margins. Within that balance, the role of the lubricant is decisive. It is not just oil, but an agent that reduces friction, cleans the residues generated during combustion, seals the gaps between the piston rings and the cylinder, and helps stabilize the internal temperature. In a heavy engine, it circulates in large quantities and is formulated to withstand high pressures, intense loads, and temperatures that in many other engines would cause immediate degradation. The key is that this lubricant is distributed precisely to every critical corner to form a resilient film between the metallic surfaces. For that protection to be effective, a system capable of delivering it consistently and accurately is indispensable, and that is where the oil pumps installed in truck engines come into play, which stand out for their capacity and the pressure they can generate, maintaining a constant flow to the bearings, crankshaft, connecting rods, pistons, and camshafts, even under conditions of enormous demand. Thanks to that stable pressure, metal does not come into direct contact with other metal, which prevents wear that would be devastating in the long term. In addition, the continuous circulation of the oil not only preserves the friction surfaces, but also helps moderate the accumulation of heat in the most stressed areas of the assembly. However, this partial thermal control requires a complement capable of managing the heat produced constantly by combustion, a function assumed by the cooling system in truck engines, where the heat generated is enormous and must be evacuated quickly through a circuit of coolant that flows through internal passages in the block and cylinder head. This liquid absorbs the heat and conducts it to the radiator, where it dissipates before starting the circuit again, thus maintaining a thermal balance that is decisive for the longevity of the assembly. When the temperature remains stable, The materials do not suffer abrupt expansions or sudden stresses, and the oil retains its properties for longer, which reinforces the overall durability of the engine. In this way, lubrication and cooling do not act as isolated systems, but as parts of the same protective mechanism that keeps the engine within safe operating conditions, while the lubricant separates the surfaces and reduces friction, and the coolant controls the temperature of the assembly, preventing the engine from entering critical zones where wear could increase exponentially. Moreover, the oil itself helps carry away impurities and minimize deposit formation, which is essential in an engine that burns fuel for hours on end without rest. A clear example of the effectiveness of these systems can be seen in a truck traveling hundreds of kilometers in the middle of summer, where the engine works for hours climbing slopes, maintaining speed with a heavy load and facing high external temperatures. Even so, the temperature needle remains stable and shows no abrupt changes while the oil flows smoothly, creating a protective film on every critical surface, and the coolant dissipates the heat without difficulty. This operational stability is what allows the engine to continue functioning normally even after covering distances that would challenge other types of machinery. But even with a robust structure and systems capable of maintaining internal balance, the environment in which the engine operates also plays a decisive role. And here an interesting nuance appears that leads us to the next point. What is special about the way trucks usually operate on the road that contributes so much to engine longevity? The key is not only in how these engines are built, but in the type of mechanical life they lead. Unlike other vehicles subjected to constant variations, long-distance trucks operate for hours in stable and prolonged conditions that significantly reduce unnecessary stress. This almost monotonous environment, far from being harmful, is surprisingly beneficial for all their internal components and constitutes one of the least visible yet most decisive factors in explaining why they reach such high mileage without the need for major interventions. This difference becomes clear when comparing its routine with that of a light engine, which must face an unpredictable environment daily, marked by cold starts, rapid accelerations, abrupt braking, urban traffic, short but demanding climbs, and constant stops, situations in which every change entails thermal and mechanical impact. In contrast, the engine of a truck that covers long distances spends hours at an almost fixed regime, where cruising speed is maintained, the required torque is similar over long stretches, and the revolutions remain within a narrow range, far from the engine's maximum limits. When operation remains constant for hours, a less visible but decisive advantage emerges: thermal stability, because an engine that repeatedly oscillates between cold and hot forces its materials to expand and contract, generating micro-fatigue over time. In a truck, however, the temperature is maintained at an optimal level and avoids that cycle of repeated stresses, allowing the oil to work within a stable viscosity range, the cooling system to avoid abrupt changes, and the metallic surfaces to remain in a predictable and controlled environment. This same continuity is reflected in the way the engine delivers its power, spending most of the time within its efficiency zone, without needing to react to sudden demands or suffer accelerations that disrupt its internal rhythm, so that torque remains constant and revolutions stay within a range that does not compromise the moving assembly. Pistons, connecting rods, and the crankshaft thus operate within a balance that favors their preservation, turning this regularity into a clear advantage over engines subjected to a much more variable usage cycle. It is enough to imagine a truck moving at night on a highway, maintaining a speed that barely varies while the engine sustains a uniform cadence, and the load being transported requires constant torque for hours, to the point that long stretches can pass without the rotational speed changing significantly, as if it were operating in an almost stationary state without jolts. But even with such a favorable operating environment, longevity does not depend solely on a stable regime, but also on how that use is accompanied by technical and professional decisions over time, because even the best designed engine needs more than consistency to maintain its optimal condition after thousands of hours of continuous operation. Real durability is not improvised. It is built kilometer by kilometer through a discipline rarely seen from the outside. That discipline has little to do with the conventional maintenance that a light vehicle receives, because in heavy transport everything follows strict routines, planned procedures, and constant checks aimed at anticipating any sign of wear before it becomes a major problem. consolidating a technical culture that prioritizes prevention over reaction. In that context, fleet maintenance acquires its own logic, which does not rely on intuition or sporadic interventions, but is based on organized programs capable of determining when to check each part of the engine, how to assess its condition, and what actions should be taken according to the type of service each vehicle performs. This includes periodic inspections in which the condition of the lubricant, filters, and injection systems is checked, as well as all those elements that keep the heart of the truck alive and healthy. Within that logic, a decisive nuance appears. In heavy engines, maintenance is not guided solely by kilometers traveled, but also by actual hours of operation, a criterion that better aligns with the way these vehicles work. A truck that spends hours on the highway maintaining a stable regime can cover hundreds of kilometers without its oil suffering wear proportional to the distance. So by measuring work in hours, it is possible to estimate lubricant fatigue more accurately and plan changes at the appropriate time, aligning maintenance with the engine's actual effort. In that same line of anticipation, periodic analysis of the lubricant becomes a decisive tool for interpreting what is happening inside the engine, because companies send oil samples to specialized laboratories where the presence of metallic particles, combustion residues, and any contaminants that may indicate internal wear is examined. This procedure allows problems to be detected even before visible symptoms appear, so that if a component begins to deteriorate, the analyses reflect it in advance and make it possible to intervene before the problem escalates. But that technical monitoring is not limited to the oil, because professional maintenance extends far beyond periodic fluid changes and incorporates calibrations, adjustments, and systematic checks of multiple systems. Technicians check injection pressures, component tolerances, and the stability of auxiliary elements, evaluate the conditions of the cooling system, and verify that sensors are working correctly so that each inspection becomes a key moment to keep the engine within its ideal parameters. Behind that technical structure, there is also a human criterion that ultimately supports the whole system. Drivers and mechanics not only execute procedures, they also constitute the other half of engine care. They know how to interpret noises, sensations, and variations in the vehicle's behavior, and they understand how a heavy engine should operate and when something is out of place. That direct experience is usually what makes the difference between a small warning and a major problem, and it is in that human judgment that the true longevity of these engines is consolidated. Engineering can be exceptional and maintenance can be programmed down to the millimeter, but without the intervention of those who operate and care for these machines every day, none of that would achieve the same result. In that daily intervention, the driver occupies a decisive role because they spend hours behind the wheel and develop a special sensitivity to interpret engine behavior. An experienced professional notices changes that would go unnoticed by others, recognizes a strange sound at idle, detects a slight vibration in a constant gear, perceives a different response when accelerating, or a subtle variation in operating temperature. This perception does not arise by chance. It is formed through thousands of kilometers of experience and a deep understanding of how a heavy engine should behave when in optimal condition. Moreover, the driver knows how to manage the engine without stressing it. They maintain the appropriate regime, avoid unnecessary accelerations, shift gears smoothly, and anticipate extreme load situations to avoid demanding more from the engine than necessary. They understand the value of maintaining a constant speed over long stretches, and recognize that a sudden change can disrupt the engine's internal stability. This way of driving not only reduces wear, but also helps the lubricant and coolant perform their functions more efficiently. To that road sensitivity is added the technical insight of the specialized mechanic, who complements this work with attention that goes beyond the obvious. In the workshop environment, this experience manifests as an almost organic understanding of the engine, capable of interpreting every stain, every smell, and every wear pattern. When a driver arrives with an impression or a comment, the mechanic translates that information into a concrete action and can detect an injector beginning to lose precision, a bearing showing the first signs of fatigue, a component whose clearance suggests an imminent adjustment, or any indication that anticipates a major problem. From this constant interaction arises a virtuous cycle in which driver and mechanic complement each other. The former contributes direct usage experience, a sensitivity honed by the routine of the road and practical knowledge of vehicle behavior, while the latter adds deep analysis, the ability to interpret data, and the skill to intervene with precision. Each inspection becomes a conversation between two specialists who know the machine in front of them in detail, and when that relationship works, the engine reaches levels of longevity that surprise even those who work in the sector. In the end, the reason why many truck engines far exceed 1 million kilometers is the result of shared work in which the internal systems protect, engineering provides resilience, and maintenance ensures stability. But it is the people who close the loop, who know when to lift their foot, when to listen to a noise, when to anticipate an intervention, and when to stop to prevent greater damage. Behind those engines that surpass 1 million kilometers lies a balance built with precision. It involves engineering oriented towards strength and stability, internal systems capable of protecting the engine during endless hours of work, and an operating approach that favors consistency over abrupt changes. From the silent interaction of all these factors arises a durability that seems to defy wear. It is no coincidence. It is a combination of technical decisions, work routines, and real experience that turn these engines into companions of millions of kilometers. That mixture of science, craft, and discipline is what keeps the heart of each truck alive as it travels the roads without pause. If you have made it this far, it is because you are interested in understanding how these machines work and everything that happens beyond the obvious. This is just one of the many aspects that explain their longevity, and there are still pieces to fit into this map where engineering, routine, and human judgment intersect every day. If you found it useful or interesting, a gesture as simple as leaving a like helps the algorithm bring it to more people who share this same curiosity. And if you want to continue exploring the world of heavy transport, you can join to not miss what comes next, because there is still much to discover.